think we are going to use in our electronic devices? This crystal or this crystal? Definitely not this crystal, but this one. If you want to know about the application, circuit, structure, and history, please follow me to the slides and lab, and I will explain all of them to you. In electronic devices, we need crystals because we need to have some frequencies or some clocks in order the electronic devices to work. For example, when you are watching a video on YouTube, you need to have the crystals for sending the frequency. It needs some specific frequencies to show you videos on the LCD. So in some industry, for example, you can see in the computing, automotive, industrial, medical, telecommunication, and also the defense. Some of the application in the daily basis you can see in medical devices, in microcontrollers, in microprocessors, in gaming, in sensors, disk driver, many type of things you can see because all of those need to work. But the crystal that we are using in these days is very different from the crystal which we have used before. As a result, you need to know about the history and structure of the crystal. We need to have a stable frequencies. As a result, we need to have a crystal oscillators. Before this type of crystal, the radio station was controlled with the tuned circuit, which led to drift off some frequency really easily. So what is the tuned circuit? As you can see in this picture, it is showing you this type of circuit. You have the inductor and also you have the capacitor in here. As you know, the capacitor is always charging and discharging, and the inductor is making a magnetic field. As a result, the current is changing the location from the capacitor to the inductor and vice versa. And in this picture, you can see how each scene is working. For example, here on this picture, it will start. This is the zero part, and it will increase really slowly and to the top of it. This area, this picture is circled with the green. You can see this is the maximum of it, and this is the top of the sine wave. And after that, it will decrease it. So we need to have the sine wave as an alternative current because the job of the crystal oscillator is to converting the DC to the AC because we need the AC to have the frequencies. So this is the structure of it. We have the charging, discharging, charging, and discharging. But in the real cases, in the real world, we don't have only the capacitor and inductor. We have the resistor here. So the resistor job, as you know, is just taking a current, and when the current is really high, it will take it until there is no enough current. As you can see, the sine wave at first is it has a really good frequency, but at the end, because of the resistor, we have the damped current. So as a result, this one is not oscillated, and this doesn't have any oscillation. We are using the piezoelectric in our crystal. It is discovered in the 80s, and it is used in 1925 in the flagship. So what is the structure of it? As you can see in this picture, we have the piezoelectric, we have the crystal on it. This one, the property of the piezoelectric is that when we are applying the external stress to it, it will generate voltage for us. But you need to know the reason how this one is working. So as you can see in this picture, when I'm applying forces, it will show a voltage for me. So as a result, we will have the mechanical stress. When we have the mechanical stress, it's producing the electrical charges, and the other side, when we have the electrical charges, it will produce mechanical stress for us. This one is used in many medical devices, and medical devices have the piezo material in it, and after that it has amplifier, and the doctor can get the frequency and diagnose the problem. You need to know about the crystal, about the structure of it. Crystal is a solid, and the molecules are in high order in it. As you can see in this picture, when you also rotate this picture, you can see they are really ordered, and they will make a hexagonal shape for you. And here we have a dipole here, because we have oxygen and we have a silicon here, and oxygen is the smaller molecule, and it tends to have the negative charge toward it. When we compress and decompress the molecule, it will give us a polarization, and as a result it will produce voltages for us. Just let's see, instead of these molecules, we have the positive and negative. We have the cells in it. Each cell has a positive and negative. When the number of the cells is going up, we have a higher thickness, and that's the thickness is related to the thickness of the crystal. As you can see in this picture, when we have the thinner cut of crystal, we have the higher frequency and less net voltage. Also, when we have the thicker cut of the crystal, we have a lower frequency and high net voltage. We have different types of substances in our crystals. So we have the Rochelle salt, which has a piezo effect to the greatest degree, and also we have the quartz, which has a mechanical strength. So most of the time we are using quartz because we need to have the mechanical strength. So the crystal is just used for frequency determination of the device. But what is the oscillator? Oscillator, when we are having a DC voltage, we are converting it to the AC voltage. As a result, we are producing a periodic sine wave or square wave. We need to have our waves to go back and forth in the regular speed. As a result, we need to have the oscillation. We need to have our frequency to be oscillated. So we are using the crystals. The crystal in our devices such as TV, radio, we are using all of those. This is the schematic part of the crystal. As you can see, this is the crystal holder, and also this is the crystal. Now let's talk about the circuit of it. When we put the resistor, inductor, and capacitor on a series in a circuit, we are just representing the vibrating crystals in our circuit. This is the vibrating crystals. Now, when we are put the capacitor in parallel to the RLC, we are representing the crystal holder in it. Prior to the crystal, they used this type of circuit, but this type of circuit was not that much stable. It didn't produce a stable frequency for us. Let's see why. We have the Q factor here. The Q factor, as you can see in this picture, for the LC circuit, we don't have a really good one. We have a 2000, but for the crystal is 30,000. As a result, the Q factor is better, and they have a better frequency stable, and they are very narrow. They have very narrow bandwidth. As a result, the crystal is more energy efficient in our circuit. You can see in this picture, we have a really great frequency stability. Also, crystal oscillator and crystal resonator. They are both same, but there is a little bit difference between them. For example, the crystal oscillator, the frequency range is higher, is 10 kilohertz to 100 megahertz. Also, the output of the crystal oscillator is higher. It has a more stable frequency, but the tolerance of it is really lower than the ceramic resonator when we have the shock or vibration. As a result, for example, in a crystal oscillator can be used in application such as high-speed serial port communication, or when we have the RTC timekeeping or wall clock. The application of the ceramic resonator is microprocessor, is the low-speed serial port communication, and it's not really good for the RTC and those kind of things. Now it's time to know how to test it and how we can use it in our real life with the multimeter, with the oscilloscope, and those kind of things. Now let's test the RTC clock oscillator with a multimeter. For this one, you need to have the multimeter. The multimeter should be set at the frequency or Hz, and the board you are using it needs to have the RTC on it. On the multimeter, you have two probes. One of them needs to be connected to any part on the board that has a ground, and the positive of it needs to be connected to any pin of the crystal. When it is showing a number on the multimeter, it is showing you the number of the frequency, and it's showing you the crystal is working. Another one, when you want to test it, you can use the oscilloscope and function generator. How this one is working? So here you have the oscilloscope and you have the function generator. You need to connect the ground of both, and after that, for the positive of the oscilloscope and the function generator, each of them need to be connected separately to each pin of the crystal. That's the connection. But when you are playing with it, for example, on the crystal, it is giving you, for example, 4 megahertz. When you are sending the pulses, when you are sending the frequency with the function generator, if the frequency of the function generator and crystal are matching, the voltage or the amplitude is increasing on the oscilloscope. When they are mismatched, the amplitude will drop. This is another way of testing of the crystal. Next, we can use the IC SN7404. This is the IC you can use, and this is the circuit of it. There are also other ICs. They have the same function as this one. I have provided number here, and you can see in this picture that we need two potentiometer of kilo ohm, and also we need to have the capacitor 22 picofarad to 100 nanofarad. So you need to put it between the number 1 and 2, and after that you need to connect the crystal to the number 1 and 4, and you need the oscilloscope also to get the output, to see the output, and that will show you the number of your crystal. Till now we know about the structure and how to use it and how we can test the different type of the testing method I have give it to you. But now we need to know how we can use it in our PCB. In our PCB, just make sure that you are placed them near the microcontroller or microprocessor. As you can see in our Arduino board is really near to the microcontrollers. And another thing, the crystal routing should not have vias on it. As you can see in this picture, just make sure when you are designing a PCB, do not put vias on it. Next, we need to know how we can use it in the circuit. So in the circuit, usually you need to have the two capacitor on each side, as you can see in this picture, usually between 20 to 30 picofarad based on the need. How we can read the crystal frequency. The number is directly written on the crystals, and there is a 30 after that, and for example on this crystal you can see 16, it means 16 megahertz. And to conclude this one, the crystal oscillator is used in microcontrollers and microprocessor to generate a clock for us, because we need the synchronization in our internal operation. And in one of the example is that I2C connection. For example, in one of our video we had module max 3100, and that was connected as an I2C connection. And also in the Arduino Uno, you have a 16 megahertz on the external crystal. Another thing on the STM programming, when you are using, you have the one part which is the clock configuration, and that clock configuration is completely related to the crystal, and you can choose it and you can change it based on the module you are using, or based on the microcontroller you are using, or based on the project you can change it. I hope you have learned something new from this video, and thank you for watching.